Hello everyone, I'm Sergio Aguaci. I'm glad to present you the paper named Exploring the Robustness of Building Integrated Photovoltaic Renovation Scenarios to Climate Change Perspective. And this paper was contextualized in Switzerland. Switzerland has really ambitious targets in terms of energy emissions for 2050. The idea is to reduce 76% of CO2 emissions compared to 2005. And recently, the government announced that the carbon neutrality by 2050. In order to achieve these objectives, the building stock, the renovation of building stock appears as a key factor for that. We know that current practice and existing regulations are far from Swiss objectives, so we need to go further, and we think that architectural design could accelerate the process of linking VAPV, so produce electricity on site, with renovation of residential building stock. The approach is that new challenge appears to architects and engineers. The question is how design today, taking into account various climate evolution pathways. We know that climate change, mainly characterized by global warming, is a reality, and its effects are already visible. Increase in average temperature, increase in cloudiness, decrease in effective solar radiation, etc. So we need to integrate the concept of resilience. Resilience is generally defined as the ability of humans to adapt positively to adverse situations. And in terms of design, building design, we can use the artificial weather files that represent different possible scenarios to conduct our building performance simulation. The methodology that we use consists in 4 phases. The first one is define the renovation design scenarios, taking into account BIPV solutions. In phase 2, making an iterative process between design and simulation, using the typical meteorological weather file, DMY, with historical data, to define construction strategies, insulation thickness, etc., to obtain the final energy needs and photovoltaic performance. The phase 3 consists in simulate these scenarios, but using the different climate change scenarios, using the artificial weather file generated in this case using Meteonorm. And the phase 4, we will compare the results and take some conclusions. Phase 1 really quickly consists in definition strategies, but we define passive strategies, changing, replacing windows, increasing insulation, but also active. For example, changing the oil or gas boiler by an electric based system with heat pump, for example. This is an example. This is a case study that we use. It's a case study from 68 with 7 stories. And here you can see the current status of the building with a section of the main facade. This is a renovation scenario with indoor insulation, no BIPV that represent current practice, just to achieve the minimal legal requirements. And these 3 scenarios integrates BIPV and try to achieve more energy performance. This is an example just to say that we use also the roof, not only the facades, and we calculate the production hourly. This is the 3 climate change scenarios that we decided to use, that represent the more optimist and something in the middle. We can compare here. This left graph is the temperature We can see the temperature for the different climate change scenarios and also for different horizons compared to the TMY weather file. And also here we can see the solar radiation. The results in terms of heating and cooling demand, we can see here always comparing each renovation scenario. This is the current status. To always compare with the TMY. In this case, we can see that heating demand decreased between 70.9 and 23%, and cooling increase, reflecting this effect of global warming. We can see here the deepest renovation scenario presents less difference between 1.1 and 3.8 compared to the results obtained with TMY. This is in the case of electricity needs. And in terms of on-site PV production, the PV production in general decreased between 2 and almost 5%, depending on the scenario. Using box plots to try to see the difference between all the scenarios and variants that we simulate, we can see that the deepest renovation scenario, so S1, S2, S3, presents more concentrated results compared to the E0. So we can say that we have less variation across these climate change scenarios. The energy efficiency of a non-renovated scenario, E0, this one, depends heavily of the climate change conditions, and in that sense, E0 can be seen as less resilient. In terms of self-sufficiency and self-consumption, we can see that S2 and S3, these two renovation scenarios, including BAPV, show a greater sensibility to weather scenarios across time horizons. But the difference is not so high, and we can see that the less stable is, in terms of self-sufficiency, is the S2, but still low. It's just 2% of variation. In terms of energy balance, so we can see that the uncertainty within the renovated scenarios, with or without PV strategies, is less important than E0. Zero is always more dependent on the climate change scenario. And for S2 and S3, as using the TMY weather file, the building remains energy positive. So in general, despite the fact that the overall energy performance of the building varies, increase the heating demand, decrease cooling, results shows that if the renovation strategy were developed based on future climate scenarios, the influence would be minimal. Indeed, tendencies show no contradiction with respect to the TMY results, so in which the strategies were based. Strategies designed on the phase 1 of the methodology. So the results also serve to reiterate the importance of renovating the building stock by highlighting the important energy efficiency gains that can be achieved through various renovation strategies, some involving BIPV system. So that's all. I invite you to read the paper, and if you want to contact me, to that. Thank you very much.